Let's take a look at number 4 in section 2.5. We're just to evaluate the following limit. And as always, when you have a limit, the first thing you want to do is let's see what's happening at 5, right? If we plug in directly into this, what happens? Well, I've done that here. In the bottom, I get 5 squared minus 25, which is, of course, 0. But up top, I get 5 squared, which is 25 minus 5, which is 20. Now, the form of this limit um, is not actually indeterminate. It's not 0 over 0. We actually know what's going on here, right? In other words, the denominator here is never actually 0 because we're never actually 5. But as we get closer and closer to 5, it is getting closer and closer to 0, whereas the top is getting closer and closer to 20. And so what's happening overall? This thing is blowing up. This limit um, well, what's going to have to happen? What's going on graphically? We've got a vertical asymptote, right? We've got to go and take a look now at the limits from the right and the left, right? Because if you have a vertical asymptote, right, if this dashed line is a vertical asymptote, then you can have a function, uh, right, blowing up from values less than, let's say this is x equal 5. This vertical line is x equal 5. You can be blowing up for values as you approach 5 from below, and you can be going to minus infinity, right, as you approach 5 from above. Or you can have a situation where we're approaching minus infinity this way and positive infinity this way. Or we can have both sides going to positive infinity. And I'll go ahead and do the last case. We can have both sides what? Going to minus infinity. Okay. So when you get this form, it tells you that you have a vertical asymptote. We've got one of these four conditions. The first two conditions, we would say that this limit as x approaches 5 does not exist, right? Because one side is going to infinity, the other side going to negative infinity. In these two cases here, we would say the limit is infinite. In this case, we would say the limit's infinity because both sides are going to infinity. So the limit actually doesn't exist as a finite quantity, but we can describe the behavior and say that the limit is going to infinity. So in these two cases, does not exist. Here, the limit would be infinity. Here it would be what? Negative infinity. So we have to figure out what case we're in. You can graph the function and take a look at it near x equal 5. Um, and you can do it numerically, and I'm going to do that as well. But I first just want to, the way I would approach this is this. Taking the limit as x approaches 5 from the negative side, which means what? We're approaching 5 from below, from the left, or for values less than 5. So obviously, as we get closer and closer to 5 from below, the top is approaching what? It's getting closer and closer to 20, right? 5 squared minus 5, 25 minus 20 is getting closer to 20. The bottom is getting closer and closer to 0, yes. However, since we're always a little bit less than 5, this is never 5, right? It's always like what, 4.9, 4.99, 4.999, and so on. But of course, if you square 4.9, for instance, that's less than 25, right? So this difference, even though it's getting closer and closer to 0, is always negative, and I indicate that with that little negative. The top is always 20, the bottom is always negative. It is getting closer and closer to 0. What's that mean? Overall, this fraction is always negative for values of x close to but below 5, and therefore we're going to negative infinity. From the positive side, notice what happens. We still have that same approaching 20 up top, but on the bottom we're approaching 0, but this time from, we would say from above in a sense, right? Because the value of that we're plugging here are always greater than 5. This quantity x squared minus 25 will always be positive, right? Square 5.01, that's more than 25. This difference is positive and small. Therefore, I'm going to positive infinity. That's the way I reason with it. Of course, you can always go to the numerical uh, way of doing things. Here's the function. And remember, if I set it up to be in ask mode on the independent variable, I can plug in my own values. And here I plugged in values less than 5. Okay, 4.8, but getting closer to 5, right? 4.9, 4.99, 4.999. Look at the values. They're always negative, like I said they would be. But the absolute value, notice, is getting bigger and bigger, right? And so clearly we have a situation from the left where we're doing this sort of thing, going down to minus infinity. For values greater than 5, getting close to 5, 5.2, 5.1, 5.01, and so on, what's happening? We're always positive, as I said, right? But now notice the values are just blowing up. We're going to positive infinity. So we actually have this situation right here is what essentially is going on graphically. But what's all that mean then for the original problem, the limit as x approaches 5 of this thing? Well, it means it does not exist. And we write DNE for that. So that's what we would do. If both of these sides went to positive infinity, right, we would be in that situation. We would say this limit is also infinity. Okay, I hope that helps on this one. So it's real important to understand that when we take these limits, we're seeing what is this approaching as x gets closer and closer to 5. Okay, we really don't care what's happening at 5. In fact, in this case, we have nothing. There's no value of the function, but we do have a vertical asymptote, and that's what's important.